All right, today we're going to talk about the non-parametric version of Anova. So what happens when you do not meet, particularly the assumptions associated with skewness of normality for data. Or if you have ranked data or categorical data, the non-parametric Anova may also be appropriate as well. All right, so for basic boring Anova, the non-parametric version of that is what we call the Kruskal-Wallace. We can also use the Friedman's, but we'll talk about that a little bit later. It has special requirements for it. But the Kruskal-Wallace is very similar to our basic Anova. The post-hoc test that you would run, instead of choosing one of the post-hoc tests, you simply have to go back and run the Mann-Whitney-U test, which is what we talked about. That's the non-parametric version of the t-test. And then for a trend analysis, if you wanted to run that on data that was not normal, you could use the Juncker Terpstra, but we're not going to talk about that, just as we didn't talk about trend analysis in the parametric Anova. A little bit about the Kruskal-Wallace theory. It's very similar to the Mann-Whitney-U as well as the Wilcoxon rank sum. Essentially, you're ranking your data, and then you are reviewing the ranks and analyzing the ranks of that data and not looking at the data itself, which again is one of the downfalls of the non-parametric data, because you're just looking at the ranked data and you really don't get that description of how far apart the data points really are if the data is just ranked 1 through 10. 1 could be 15.25 and 10 could be 6,962. So there would be a substantial difference, but that rank doesn't kind of give you that information, which is really the downfall of the non-parametric version. However, keep in mind, if you are running a parametric test on data that does not meet the assumptions, that parametric test doesn't have any power either. So it's actually better to run the non-parametric in those cases. So again, you're using the ranked data. And then once you have that ranked data, the Kruskal-Wallace calculates its test statistic, which is the H value, and the degrees of freedom is just K-1. Again, you don't need to understand how to use the equation. You just have to know how to use and understand how to and when to use the Kruskal-Wallace and how to use it in SPSS. So we're going to look at a real basic example. How does eating soy affect your psych score? So we're looking at 80 males, 20 in each group. 20 males did not eat any soy. 20 males had 1 soy meal a day or per week, 4 soy per week, and 7 soy per week. And here's essentially what the data looks like. If you were to calculate the test statistic itself, you can see I added the ranks in there. Sum the ranks, and then you can calculate H is 8.659. And you can compare that to other statistical tables. But again, this class is not about using the equation, it's more about understanding how to use this in SPSS and interpret this information. So let's go ahead and throw this into SPSS. First thing that we're going to want to do is we're going to want to look at our normality and our variances. You can see that we've got some issues with normality. So the data does not appear to be very normal. And in addition to that, our variances are not normal. Now obviously for this piece up here, you would really want to look at the skewness to see if you wanted to proceed with a non-parametric or proceed with a parametric. Again, if it's just kurtosis that's off, the parametric version of Anova, it would be satisfactory. If it's your skewness that's off, you should proceed with the Kruskal-Wallace. All right, for the Kruskal-Wallace, pretty easy. I'll show you how to do this in SPSS because this is version 18. I'll show it to you in the new version. There's three tabs generally, though, at the top that we need to look at. So the objective tab, compare across groups. The fields, test field, and the group, very similar to what you would have for the Anova. and then the settings. So what type of analysis do you want to do? And here's where you get to select your Kruskal Wallace, one-way Anova, right here. You can choose other versions. You can choose the Mann-Whitney U here as well for our post-hoc test. But we're at least going to go with the Kruskal Wallace. And once you hit run, you end up with this analysis. Again, we reject the null hypothesis because the significance is less than 0.05. But it's very difficult to interpret. We know that the null hypothesis was rejected. But what does that mean? So we know the mean of no soy meals is potentially not equal to the mean of 1, which is potentially not equal to the mean of 4, which is not equal to the mean of 7. But we don't know which one of these is true or not true. We just know that at least one of them is not equal. The rest of them could be equal. So we're going to have to make some decisions and go back to doing a Mann-Whitney U to be able to figure this out. Now, if you did the Kruskal Wallace in the old-fashioned version, it actually gives you information. So you could do descriptives and get this very similar information. You'll still end up with your same significance value if you did it the old-fashioned way. So I would just go ahead and run your descriptives to go ahead and get your mean ranks. And then you can see what you really want to be able to compare to. We know that the means are not equal. That is what the Kruskal Wallace told us. Well, as you can see here, you're probably getting the sense of what the statistical significance is pulling from. It seems that the 7 soy meals per week is probably the one that's not equal to the rest. But based upon the analysis, we don't know that for sure right now. So we're going to have to run some type of post-hoc test to statistically state which is different. So when we're doing the Mann-Whitney test, very similar to the t-test, the more tests you run, the more type 1 error rates we're going to have. So depending upon how many tests we're going to run, we're going to have to use the Bonferroni correction. So we need to be very selective because we do not want to take that Bonferroni correction and take it down to some ridiculous value of, say, 0.00001. That's not, the smaller the type 1 error rate, the less likely you're going to find significant differences. So we want to stick as close to 95 as possible. So we need to be very selective when we're actually selecting what post-hoc test we're going to run. This is very similar to like the contrast. You have to figure out what you're running before you run it. So let's think about what we should do for this example. The question was, let's go back to the example question. The example question is, does eating soy affect your psych score? So if that's the question, does it matter if we compare 1 meal to 4 meals, 1 meal to 7 meals, 7 meals to 4 meals? Probably not. We just want to be able to say, does eating soy change your psych score? Well, let's go ahead and say, well, let's compare 1 soy meal to nothing. Let's compare 4 soy meals to nothing. And let's compare 7 soy meals to nothing. So we'll be able to say, maybe as you increase in soy, what happens to your psych score? And then if we're going to be running 3 tests, we can use that 0.05 divided by 3. We'll use 0.0167 as our critical level of significance. So let's go ahead and run a multiple Mann-Whitney U. And we're going to have to do this several times. So first time, we're actually going to have to go ahead and define groups. When we define the groups, we're going to have to say what we're comparing. And when you define the groups again, we're going to say what we're comparing. So we have to make sure what we know the groups are, what our factors are, as to what we're comparing. So when we run this analysis, we're going to end up with multiple pieces. So here's the multiple pieces. I'm just going to put a square around the 3 different tests that we ran. So the first test was no soy meals versus 1 soy meal. And we have the significance of 0.82, so it's not significant. So we know that no soy meals is equal to 1 soy meal. Second test, significance of 0.758. So we know that no soy meals is equal to 4 soy meals. And the last test, 0.09. So now we know that no soy meals is not equal to 7 soy meals. So don't forget that when you do this, you have to look at the significance that you're looking at. So you can't look at the 0.05 anymore. You have to look at the 0.0167. None of these values are anywhere close, but you do have to keep in mind that you have to do that comparison and not the 0.05. So essentially, our result is that eating 7 soy meals lowers our psych score. How do we know it lowers our psych score? Look right here in our mean ranks. Eating 7 soy meals brought that psych score down from 25 to 15.7. Now, if you wanted to calculate the effect size to find out what practical significance you have, you would only do that for the Mann-Whitney test and not for the Kruskal-Wallace. All right, let's move on to Friedman's Anova. When would you use this? Well, you're going to have more than 2 conditions, and we're going to have the same participants being used in all of those conditions. So similar to a paired t-test, except here we're having more than 2 conditions. So if you violated the assumption of skewness or any other of the parametric tests, Friedman's Anova can be used to be able to keep the power that you need for this test. Theory, essentially, as we've talked about with all the other tests for non-parametric associated with ranked data. So we'll look at a real basic example. Does the Atkins diet work? I changed it from what the actual name is to make it, I don't want the people to get offended. So we have 10 women, because those are the only people that generally worry about their weight. And we're going to look at the time since they began their diet, their baseline, 1 month and 2 months, to see if the diet does work. So here is our weight by person, and by start in month 1 to month 2, and the data is ranked. So we'll go ahead and look at normality. We've got a few issues with normality, so it does make sense to use the Friedman's Anova. So the Friedman's Anova essentially has 2 pieces, the exact and the statistics. Statistics, we just really want descriptives and quartiles, and we do want to run an exact test, but we do have to say how long we want that to be run. We don't want it to run forever. 5 minutes is a nice quick one. So here is the output for the Friedman's Anova. Very easy to read. Look at the significance. Much, much greater than 0.05. So it looks like everything is equal. Now, when you look at their mean, these are their mean weights. Now you see why everything is equal, because the diet did not seem to work. So that's pretty much it with the non-parametric Anova. I'll also post the how to run it in SPSS in the newest version. And after this, we'll get into analysis of covariance and other variant forms of the Anova that are more on the parametric side.